Yes.
Could you give me some information about my test? And I can review it, yes or no?
I sent you a screenshot saying the date of the test happening on the day of, that it was happening tonight. You had that information. And the week leading up to the test, we talked about it in multiple classes. And if I'm not mistaken, you attended those classes. And at the beginning of this section, we also talked about at the end of 5 to 6 class periods, we will have a test. So you were aware of when the test would be. That's 3 different ways in which you were made aware of the test date. So as far as I'm concerned at this moment, no. I'll discuss it with the government people here and with my team back home and see what they think. But at this point, no. Because you were aware, you had the opportunity. You didn't even contact me to say, I'm not going to be there, which would have been enough to say, okay, let's reschedule it. But if you just didn't talk to me, didn't contact me, then that means you just blew it off, as far as I can tell.
So you didn't know on Saturday that I was sick? Did I inform you?
It was supposed to be earlier, but because of the football, it was.
Yeah, Marco, I mentioned that I was sick.
How much?
So
I mentioned that.
yes, and the test happened a week before.
No, it was on Saturday.
No, the
No,
test was on
Monday.
Monday, 5 days before that. 5 days before
not
that. It
last
happened
week,
literally a week ago. This discussion isn't happening right now because we're delaying everybody for your
Yeah, but what's the
topic.
meaning
So
for
we're
me
going
sitting
to
here?
talk about this after class. Sorry, Jim.
Yeah. Well, you can discuss it with Sam.
Yeah.
Sam will have some ideas on all that, Chris.
Yeah. I'll talk to the professors at home, see if there's a fair way to do it, because otherwise it's not fair to the students that did come.
Okay. You see my shared screen?
Yes.
Okay. So we're going to continue with phosphates today, and then we'll move into micronutrients. And if we have time, well, after that, then we're going to talk about soil physical properties. I'm going to keep all of the points quite brief today. In the end, if we have time, we'll talk about global trends in plant protection, favoring low toxicity. It's a presentation that I do at universities and with farmer groups, and we have a long version and a short version of that. We could present at the end the short version of that. It could be very meaningful information for all of you. How many do you have there today, Chris?
4, 6, 7, 8 people today.
Okay, 8 people.
They'll filter in, but 8 now.
Starting. All right. So in the case of potassium, we've already covered the beginning steps here. Organic phosphorus sources, organic phosphorus fertilizers have been used for centuries as phosphorus sources for crops. Even with the advent of modern phosphate fertilizer technology processes, organic phosphorus sources from animal manures, including compost, are still very important. Optimal soil test levels. Numerous research projects have demonstrated that agronomic crops will respond to phosphate fertilization if soil test levels are very low. So if you got a soil test and it shows low and medium ranges are below 15 parts per million, then there's a very good chance that the crops will respond to fertilizer, to added phosphate to the field. Corn will respond to levels up to 15 to 20 parts per million. Potatoes will respond to levels up to 30 parts per million. Predicting the need for phosphate fertilizer. Phosphorus soil test measures soil's ability to supply phosphorus to the soil solution for plant use, but it does not measure the total quantity of phosphorus. The relationship between phosphorus determined by a soil test and the phosphate fertilizer requirements are developed from the results of numerous research trials that measured various rates of applied phosphate and yields. We discussed this the other day, last week, that there are nutrient requirements for crops based on the type of crop and the projected level of productivity. Now, this data is largely based on the fact that harvesting crops from a field or from a soil is a process of mining and taking nutrients out of the field. And I will remind you guys that it would be good to isolate and identify tables of information related to nutrient harvesting, how much nutrients are removed from the field for the various crops that you're working with there on your island. Deficiencies, purpling, phosphate deficiency.
One point, Jim, sorry. So I
Yeah.
found a table of approximate uses of nitrogen, potassium, and phosphorus from Florida. So it should be somewhat similar to here. So it's one document. It's in the shared folder. I put it into there's a Word document that has a bunch of useful links in it. And there it's kind of organized somewhat. So if you go into that, there is a document talking about approximate nutritional use by crop. So, sorry, go ahead.
That's good. That's good. That's good. University of Florida is probably an excellent resource. All of the publications from the University of Florida would be excellent for all of the islands of the Caribbean, including your island. Now we're going to talk about deficiencies. Purpling is a very common deficiency associated with phosphorus deficiency. In corn, you'll see it with young plants because there's a greater demand for phosphorus in the early growing season for any crop. So you're going to see it with young plants mostly. Here's what it looks like with papaya. And you'll see that it starts on the outer areas of the leaf and especially between the veins. Here's what it looks like on a tomato plant. And you can clearly see the purple that's taking place there. Here's a phosphorus deficiency on potatoes. Potatoes are very closely related plants. Here's what it looks like on a mango. Again, quality to the leaves. Are you still there?
Yeah, we lost you for a second. Hold on. I'm going to try to turn off our video and just have you up.
Okay. Have any of you seen plants on your farms with a purplish tint to the leaves? Is that something that people have seen there at all? Tomatoes, potatoes, fruit trees.
I show you. You noticed the tomato right away. Was that
Yeah,
just the
I
leaf?
noticed the leaves, yeah.
Okay. But generally, no, they haven't seen a lot of the purpling for the tomatoes. Any of the other plants? Did you guys notice anything?
Yeah.
Yeah? Which ones?
Papaya.
Yeah, papaya.
The papaya they recognized.
Okay. All right. Very good. Well, purpling of leaves is related to phosphorus deficiency. Potassium. This is also a macronutrient. It's classified as a macronutrient because plants take up a large quantity of potassium during their life cycle. The role of potassium. It's associated with the movement of water, nutrient, the movement of carbohydrates in the plant tissue, or the development of carbohydrates in the plant tissue. It's involved with enzyme activation within the plant, which affects protein, starch, and ATP, adenosine triphosphate production. ATP is the energy molecule in plant physiology, in plant metabolic pathways. The production of ATP can regulate the rate of photosynthesis. Photosynthesis feeds the ATP system in the physiological metabolic pathways of a plant. Potassium also helps regulate the opening and closing of the stomata. Potassium salts, as you can imagine, have an influence on the ability of a plant stomata to open and close. This regulates the exchange of water vapor, oxygen, and carbon dioxide. If potassium salts are deficient, are not supplied in adequate amounts, it'll stunt plant growth and reduce the yield. Other roles for potassium. It's known to increase root growth and improve drought resistance. It maintains turgor. Turgor is the pressure on the inside of a cell against the cell membrane. Turgor pressure. It reduces water loss and wilting. It aids in photosynthesis and food formation. It reduces respiration, preventing energy losses. It enhances translocation of sugars and starch, produces grain rich in starch, increases plant protein content, builds cellulose, and reduces lodging. Lodging is a problem in plants where the cells have elongated too quickly, and as the plant has grown, the plant cell walls are therefore weak, and under the pressure of wind, the plant will bend over and may lay down flat in the field. If you've ever seen, maybe you've seen this on your island, but maybe you've seen pictures of it, where rice fields, wheat fields, all kinds of grass fields, sugarcane fields, the wind will blow them down and they'll lay flat on the ground. This is called lodging. Lodging is especially a problem when we use excessive amounts of nitrogen in the production of the crop. Nitrogen causes the cell walls to elongate. The cell walls end up being too thin. They don't support the plant against the pressure of wind. Potassium combats lodging. It reduces lodging problems by making the cell walls more strong, which is related to the production of cellulose. Cell walls are primarily composed of cellulose. Stronger cell walls means less crop diseases. Chris is getting his daily dosage of potassium by eating multiple bananas today. Bananas are very high in potassium. The total potassium content of soils frequently exceeds 20,000 or 20,000 parts per million. While the supply of potassium in soils is quite large, relatively small amounts are available for plant growth. That's because nearly all of the potassium in the structural component of soil minerals. It's tied up. The amount of potassium supplied by soils varies due to large differences in soil parent materials and the effect weathering has on these materials. Therefore, potassium is an important component of your soil fertility program. There are three forms of potassium in the soil: unavailable, slowly available, or fixed, and readily available on the equilibrium in the soil system. This is the potassium cycle. Potassium is moving in the soil system and the agricultural production system. Potassium is constantly on the move. Animals can be sources of potassium, other forms of biological solids, plant residues, primary minerals in your soil that make up the mineral fraction of your soil, and the weathering of those minerals is a source of potassium. Fertilizers are a source of potassium. Potassium is removed by crop harvesting. Also, potassium is removed through runoff and erosion, through various kinds of chemical exchanges in the soil will tie up potassium. Potassium can also be leached from the soil. Forms of potassium that are unavailable. 90 to 98% of the total soil potassium is found in this form. The minerals, feldspars and micas, contain most of the potassium. Over long periods of time, these minerals weather or they break down, and potassium is released. It's a very slow process. Secondary minerals, slowly available forms and compounds. This is potassium that's in a slow release form. These forms of potassium is thought to be trapped between layers of clay minerals and is frequently referred to as being fixed between layers of clay. Clay particulates. Potassium that freely is available growth is potassium that is dissolved in water, and it is held on clay particle exchange sites, which are found on the surface of clay particles, as we discussed. This is called exchangeable potassium. This is the form of potassium that is measured in a soil test. It's also the form of potassium that plants will absorb. As soon as the soil water's potassium concentration drops, because plants are taking it out of the system, out of the soil water, additional potassium is then released into the soil solution from the potassium that's attached to the clay minerals, the exchange sites. The potassium attached to the clay mineral exchange sites is more readily available to plant growth than the potassium trapped between layers of clay minerals. Several things affect the plant's uptake of potassium, including soil moisture, aeration, oxygen levels, soil temperature, and tillage systems. Higher soil moisture usually means greater potassium availability. Air in the soil is necessary for root aspiration and potassium uptake. Root activity, plant function, and physiological processes all increase as soil temperature increases. Increased physiological activity leads to increased potassium uptake. The optimum temperature for potassium to be taken up by a plant is 60 to 80 degrees Fahrenheit. Potassium uptake is reduced at low soil temperatures. Soil test for calcium is the best management tool for predicting the amount of potash needed in a fertilizer program. Potash is a word to describe a source of potassium. It's a chemical form of potassium. Available potassium in soils is estimated by measuring the soil of total of solution potassium and the exchangeable potassium. The relative level classifications estimated in a soil test are as follows: low and very low ranges. You can expect an increase in production if you add potash fertilizer to a fertilizer program. If the test shows low or very low range, medium and high range, adding additional productivity or added yield may or may not be observed if you add potash or potassium. That depends on the type of crop that you're growing and the demand for potassium by the crop. High and very high range, you should not expect to see any response if you invest money to add potassium or potash to your soils. Sandy soils with a low cation exchange capacity have a low ability to hold potassium. Consider potassium to be partially mobile on sandy soils. That means that you can lose the potassium very easily to leaching. And you need to apply it closer to the time of planting, just before planting. Here's what potassium deficiencies look like. This is a papaya. This is an ornamental tree. This is an ornamental tree. Another ornamental tree. This is a mango. Have you seen this? This is a mango with potassium salt deficiencies.
On the mangoes, for sure. I've seen that.
Yeah. Cucumbers, you can see on the outer edge the development of a chloritic condition, which is a symptom of potassium salt deficiency. Here it is on a tomato plant. On the outer edges, you can see the development of a chlorosis of the leaf, which is a symptom of potassium salt deficiency. Here it is on a potato in a much more severe state. That you can see the outer development of chlorosis of the leaf, which is the symptom of potassium salt deficiency. All right. At a later point
Got a
in
question here.
yes,
It's, if you're seeing right now, potassium on the leaf, it's just, you see it on the outside of the leaf. And that's what we're talking about another disease, to see it in the center of the, is there some standards about where to see what kind or where it's coming from, based on where it starts?
Yeah, sure.
Maybe
So we're noticing that a lot of the potassium deficiencies start on the edges, and the nitrogen had, its own pattern. Is that a commonality for many nutrients, like different nutrients? If you can you differentiate
Yes, it is.
deficiency in a disease, for example?
Yes, it's it's not exactly an easy thing to do, but developing some skill at identifying deficiencies is important. It normally looks a little different from diseases, and learning how to differentiate between the symptoms on the leaf that are related to nutrient deficiencies compared to symptoms on the leaf that are related to diseases. This is a talent that you will have to develop, and it's part of the art of being a farmer. Does that make sense?
On nitrogen,
One second.
potassium, can we make one relation of where it should start? See when it's nitrogen, where it's potassium, leaving out diseases. Just,
Yeah. So I mean, if we look at the nitrogen part of the
yes, it
of
should be
this
in the
presentation,
center
it
of the-
usually starts in the middle
Yes.
versus where potassium starts on the edges. And Jim's bringing it up. Here we go. So so it starts along the main veins in the center, and focuses mostly on the main veins, whereas potassium starts on the leaf edge and works its way in. So I actually saw the exact thing of the mango picture. I saw that exact thing at Lucian's farm. That's exactly what it looks like. So, is that good? All right. Yeah, we're good. Oh, wait, one more.
Okay.
Chris, is there a way that we can add potassium to the ground in an organic way? For example,
Yeah. So the next lecture, we're going to have Steve back, and he's going to talk about ways to get organic sources of nitrogen, potassium, ways to integrate it into your soil, how to use organic sources to fix these issues. So Steve's aware of what we're talking about. I talked to him today. He's preparing to follow up right behind this with ways to address these kinds of things, and also going to talk a little bit about less, micronutrients. Less quantities are needed, but they're still very important, and where to source those too. So we'll talk about it. A couple more questions. Yeah.
Is it the intention that
All right.
every crop you yield, you do the test? Would that be something that you recommend?
A soil test?
Yes.
No, so you don't necessarily have to take a soil test. Actually, it's not recommended really to take a soil test every time you harvest a crop because it gets expensive. Most farmers will do it maybe once a year, and that's pretty good, like a good regimen to be on. Some farmers will go to every 2 years. Some will do it every 3 or 4. You could base it on how intensive your cropping system is. Eventually, for example, if you know that your crop takes a lot of potassium and nitrogen from your soil, and you have several soil tests in a row that say, my crop removed this, I should add this back. And then when you add it back, it comes back to where you thought it should be. The same crop removes it again. Then once you start to see on your ground with your soils the kind of inputs you're using, it becomes less important to take that test every time because you have the data on your ground supporting what you already need to know. So then soil test is important, but not as regimented potentially. If you know that this crop takes this much nutrient, then you can develop a fertilization regiment, so to speak. Something that, all right, after this crop, I fertilize with this because I know I'm short on this nutrient now. And then you could even go so far as, all right, I harvested this many kilograms of this crop, which means in theory I took this much potassium, this much nitrogen, this much blah, blah, blah. I mean, you can depends on how fine a detail you want to get to, but taking a soil test, generally speaking, once a year is good practice. Do you agree with that, Jim?
Yes, especially in horticulture. In grain farming, it's probably more like every 3 or 4 years. But probably most of the time with horticulture, it's more easy to justify the economics of soil testing more frequently. As Chris mentioned, you know, it costs some money. So, and it could be that you are all going to have access to some simple soil test methods there and kits whereby the cost would not be too high. Even though the data is pretty much qualitative, that's okay. At least it's good to keep track of how your soils are doing. On an annual basis, it would be ideal to do it on an annual basis. And the more data that you have in front of you about how your soils are progressing as you use them to produce your agricultural economy, it's very valuable to produce that data. Figuring out how to do it as cheaply as possible is really the job of the management. So, Chris, you're going to be helping them figure out how to find access to soil tests as cheap as possible.
So one of the things we're going to do is run a soil test for every farmer in the course, just so they can start to understand where they're at.
Very good.
So it'll be a beginning, and then the test will stay here. We'll train up probably the mentors to do the tests, and then as we go along, we can see what's needed. Another question.
It might be interesting.
Go on.
It might be interesting to take those soil test results and pull 3 or 4 of them, and in one of your seminars that are planned in the next coming months, that you have maybe a couple of people like Steve and I could address those particular soil tests, 3 or 4 of them, and discuss how the farm management system for that farm should approach the issue of managing the test results that they see in those specific test measures, something like that.
One of our already sent me his soil test. It's an old one from like 2010, but maybe I could pass that on to you or Steve, and we could look at it maybe for Steve, and just have a look at it, if you'd be okay with that. Roel?
Yeah, if you, let's say, if you naturally, with using organic material, you add phosphorus, nitrogen, and potassium to the soil, would you have to do a test to keep measuring it? Because can you overdo it? Can you do like put too much?
Yeah, you can definitely overdo it. You know, if you add NPK to your soils using organic methods, can you overdo it? Do you need a test, or basically, can you overdo it, and what's the consequence of that?
Okay, it's a question of probabilities. In organic farming systems, the type of raw material that's commonly used, the probability of overdoing it with plant foods, plant nutrient materials, the probability is very low. With chemical farming, it is possible to overdose, especially with respect to nitrogen. Overdosing when nitrogen produces some very significant problems in in plant metabolism and how the anatomy of the plant develops. And so you don't want to overdose with nitrogen for sure in conventional agriculture. P and K you're less likely to produce problems with those elements.
Okay, good. I mean, one thing that we talk about a lot is using compost for our fertility back home. That's one of the more stable versions of fertilizers you can use. I mean, it's already done its composting. It's already broken down. It's in a, like we said, mostly not going to degrade form, I think is what we talked about a little bit earlier in the soil science section. So compost is a great way to do it, but there are other sources which Steve will talk about next lesson. Anyone else?
Yeah.
Okay, I think we're good.
Okay. So now we're going to talk briefly about secondary and micronutrients. This first section is periodic table on crop nutrients. There are 17 nutrients that are essential for plant food. Optimum yields can be produced when all these nutrients are in proper supply. If just one nutrient is lacking in the soil, crop yields will suffer. Understanding each nutrient's role and value will ensure your crops will thrive, producing maximum yields. We've largely been talking about the macronutrients here of nitrogen, phosphorus, and potassium. The secondary nutrients are magnesium, sulfur, and calcium. The number that you see here beside the element is the position of that element in the periodic table. Sure, all of you at one point or another seen a periodic table. If you have not, I would suggest that in your learning center there for agriculture, that you get a periodic table, one of those charts, which is a poster of the periodic table, and put it on the wall there someplace, so people can see these elements and understand them from the point of view of the periodic table itself. The micronutrients are boron, chlorine, manganese, iron, nickel, copper, zinc, and molybdenum. Non-fertilizer elements include hydrogen, carbon, and oxygen, which come from the atmosphere. Calcium, magnesium, and sulfur. Although calcium, magnesium, and sulfur are considered secondary elements, they are just as important for plant production as any of the other 14 essential plant nutrients. The comparison of total calcium, magnesium, and sulfur that are removed by a crop. This is the crop taking these elements out of the soil. This is calculated in terms of pounds per acre. On your island, do you use pounds, or do you use the English system of pounds, or are you totally metric?
Metric.
They're metric.
Okay, so 1 kilo is 1 pound per acre is roughly equal to 1 kilo per hectare. It's a very easy conversion. For many of the measures, especially this one, it's a fairly easy conversion. So this is roughly equal to 1 kilo per hectare. And you're measuring your land in hectares, yes?
Yeah, that's right.
All right, good, good. So you can see the list here. Some of these crops will be related to your local production, including tomatoes, onions, maybe peanuts, maybe certain types of beets, certain types of grasses that you might use there. And you can see the removal of elements like calcium. We'll look at calcium as an example. And the volume of kilos per hectare for a certain level of yield. And these are English measurements of yield, but it can be converted if you need to. But the main point here is that at these basic yield levels, which are pretty common yield levels, this is how much calcium is pulled out by that crop. So you can see it's quite a bit per hectare. So imagine that you were growing tomatoes and it pulled 30 kilos of calcium out of your field per hectare. Ideally, you should be replacing that calcium. So Chris, I mean, you know the world of corn and soybeans. How many farmers do you think are replacing in their corn and soybean rotations in Iowa, where we live? How many of them are replacing the calcium that's being taken out of their fields?
A very small handful.
Very few.
I mean, I know of a couple progressive farmers. One of the people that we rent our ground to at home, you know, they're very good. They take soil tests every year, and you know, they have their applications of minerals that are, you know, broad spectrum, not just the NPK. And I know of one
That's good.
guy that's about my age, but doing large scale ag, that I think he actually did won like a yield competition nationwide for Monsanto. Got something like 400 bushels per acre, something freaking absurd.
Yeah.
But he was using, you know, micronutrients to do it, is what I understand. He really dug into his soil test and like applied it perfectly over a scale and got that yield result. But that's two of hundreds, thousands of people.
Yes. So, you know, it would be good to understand the crop that you're growing, the amount of these nutrients that are being removed from the field, and to think how you're going to replace them. And there are many sources for replacing calcium. It could be that Steve will cover most of this with you, but around the world, you'll hear of all kinds of methods to replace calcium. I've been in the Middle East where they're using bones. They grind them up into a powder and they use bones to replace calcium in agricultural field. Other places use shells. There's a whole industry of excavating shells along the coastal regions of the oceans and using those shells to build roads and also as a calcium source in agricultural fields, and also as a calcium source for animals. Dairy animals require quite a lot of calcium contributions because milk is high in calcium. When you milk the cow, it takes the calcium away from the cow's bloodstream, and that is a problem for the cow. So you have to replace the calcium. If you're doing it for your cow, I can tell you you would be really smart if you were also doing it for your tomatoes.
So something, I was visiting a beach on Sunday, and I noticed as we were driving out, there was a pile of like coral and rocks where they had like taken it off the beach and just dumped it to get it away.
Yeah,
And I wondered if that was actually a source of calcium, you know, something that could be ground up and used.
absolutely it is.
So a waste product, something that you guys have, you want to get rid of, something you can use.
What about seawater itself? Because seawater contains a lot of minerals.
What about seawater, Jim?
Seawater is not really a source of, well, it is a source of nutrients. There's no question about it. The problem is the sodium content tends to be really high, and seawater really is only adapted as a source of irrigation water for plants that are sodium tolerant. They're saline tolerant. And there are plants that can handle a certain amount of seawater as irrigation. And seawater does have, you know, some micronutrients blended in with it. Seaweed. You ever see seaweed wash up on the beach there?
Yeah.
Pickle.
All right. Well, I would collect all of it because it's a very, very potent nutrient material, and it contains seaweed has about 80 different micronutrients in it, and it also has potassium in it. It runs about 4% potassium.
Wow.
Can you dissolve the water and the salt water?
Sorry, another question here?
Can you dissolve the salt water? So mix it with just water to reduce the content of sodium?
Yeah, so salt water, I've heard of salt water used as a source of micronutrients in a very dilute form. But if you use it regularly, you're just going to salt your soil and make nutrients unavailable. So in some forms of agriculture, they do use it, but it's dangerous if you overdo it. The seaweed is something that you could either ground up and apply as a powder into your soil and let your nutrients or your soil biology take care of it. You could actually put it into a compost pile and let it digest there and then spread your compost. That'd be a great way to do it. You could also ferment it and then apply that foliarly or as a soil drench to get the nutrients out of it that way.
I read in the newspaper that sargassum may contain heavy metals.
Which one?
Heavy metals, sargassum.
That's
Seaweed. Oh. Oh, seaweed may contain heavy metals. You know anything about that, Jim?
That would depend on pollution in the water, and probably you're not dealing with that problem there.
So potentially, but probably not that big a deal. If you were super concerned about it, we could run some soil or some tests on it, but that kind of runs into the same issue of running soil tests in general here. So most likely not a problem.
Yeah, the odds, the probability of heavy metals being a problem in seaweed in your location is extremely low. If you were collecting seaweed on Long Island at the mouth of the Hudson River in New York City, there may be some reason to be concerned, but not where you're located.
Maybe don't collect it from around the refinery.
Yeah.
That might be the best idea.
Maybe, yeah. But even they are probably not really dumping heavy metals into the ocean.
Right.
Let's hope not.
Another question here.
It's kind of a complex question. How is the minerals? How is it the molecule bound of the minerals in seawater? How is it? Is it like present?
All right, so given that seawater contains 80 different kinds of micronutrients, how are those nutrients held in the water? Are they bound up to salts? Are they just floating around? Can you elaborate on that at all?
If you remove the salt, you remove also the...
Yeah, if you filter the salt, do you filter everything else?
If you're going to, the way that salt or sodium is removed from seawater to make the seawater usable as fresh water, will remove other elements, or it will separate those elements from the H2O. So separation, we would say removal means that when you have these water filtration systems that clean seawater as a water source for population, the waste from that process is where all the minerals are located.
Yeah, salt is one of the more difficult things to remove from water. So if you can
Yeah.
filter out a lot of other things, and salt will still stay in it. So that's why reverse osmosis is one of the few ways to get pure drinking water out of seawater, because it's such a, I mean, it's designed to remove the smallest particles in the water itself.
So let's say if you have, let's say, a gallon of water, how much seawater can you put into a gallon of fresh water without it being negatively affected on the plants?
It depends on the plant. I mean, that's a more exact question than we probably can address. If you, let's see, I mean, as he said, it was if you have a gallon of fresh water and you start adding seawater to it, at what point does it become detrimental to the plant?
That will depend on the plant and the plant's tolerance of sodium, and that would require some investigation.
I know that some forms of farming dilute seawater like 1 to several hundred parts to try to get micronutrients out of it, but not oversalt their soil. So I can point you to a few sources if you want to start researching that.
If you're thinking about micronutrients from the ocean, I think you should think in terms of the plants that grow in the ocean. Yeah. Because those plants are harvesting the nutrient content of the seawater is being harvested by those plants. Those plants are obviously very salt tolerant. And when you harvest those plants, you get a very rich source of a broad spectrum of nutrients. In talking about ocean originated nutrient material for agriculture, I would focus on the plants that grow in the water.
All right, let's move on to the next section.
Okay. Micronutrients are essential for plant growth and play an important role in a balanced crop. They include boron, copper, iron, manganese, molybdenum, zinc, nickel, and chloride. They are as important to plant nutrition as primary and secondary macronutrients, though plants don't require much of them. A lack of any one of the micronutrients in the soil can limit growth, even when all other nutrients are present in adequate amounts. And the soil test that you're going to be doing at this stage will not give you much information about these, but as the agricultural economy develops there on the island, it would be good to bring onto the island, if you, as a government service, the capacity to not only measure the macronutrients through the soil test kits that you will have, but you should plan to have the government invest in the kits that will measure these micronutrients. These kits cost more money than the kits that measure the macronutrients, but it would be a worthwhile investment for the island. And you do not have to measure micronutrients as often as you do the macronutrients. Advantages of foliar sprays. This is a common way of delivering micronutrients. Because you don't need a large volume, you can feed them directly through the stomata of the leaf, and application rates are much lower than rates for soil applications. You can get a very uniform application. The response to the applied nutrient is almost immediate. so deficiencies can be corrected during the growing season.
Thanks for yours.
And how many of you are using foliar applications today?
What are
Foliar sprays are when you apply a nutrient, either water or micronutrients, directly to the leaves. So foliar, the foliage of a plant, you're spraying the foliage. So 2, 3 people, a few people.
Okay. So this is something you're going to want to teach them, Chris, and demonstrate a lot.
Yeah.
Especially when it comes to these micronutrients. It's really the most cost-effective thing to do is just to spray the plants. And in horticulture, spraying the plants every week or every 2 weeks is not out of the question. It's quite possible economically to make that investment. Spraying seaweed extracts, which are salts basically that are taken from the seaweed, and mixing with water and foliar feeding them onto the plants and doing it on a regular basis, you get that broad spectrum of micronutrients that comes from the ocean. You get potassium as well, and seaweed itself has about 80 different micronutrients in it. And it's an excellent thing to do in a horticultural situation, horticultural cropping system, is to foliar spray these micronutrient mixes based on seaweed extracts to your plants about every 2 weeks.
So this is something we've demonstrated making like an extract from healthy soils, because we just haven't had a good example or a good compost to work with yet. But it is something we've demonstrated, just the very simple things. Now that I've found a few composts, we might start making some compost teas and doing that. We have a couple questions on this though.
I understand you need to make an extract out of the seaweed that you collect, or you can just lay it on the soil. How do you bring it easily to the plant?
In this way we're talking about it, a foliar spray is you dissolve the seaweed into water somehow, and then you spray that water directly onto the leaves of your plants, where it's uptaken very easily. And this is actually something I've been beating around in my head and can't quite justify rationally yet, Jim. How exactly do the nutrients get uptaken? Because I can think about it as far as biology, colonizing the leaves. And I understand the stoma on the bottoms of the leaves and even the lesser ones on the stems, but it doesn't seem as if that's enough to really, can you comment on that a little bit more?
Sure. The stomata of the leaf open mostly at night when the sun is down. During the day, the plant makes a anatomical adjustment and pushes water into the specialized cells that are lining the rim of the opening of the stomata, and they increase the turgidity in those cells. They relax the turgidity when the sun goes down, and the plant actually becomes, the leaf surface of the plant becomes very porous. And when you're spraying these nutrients, Chris, the answer to your question is water solubility. The plants will take up water through the porosity of the leaf during those hours when the sun is not so brilliant. And because these micronutrients or any other nutrients that you're working with or any other chemistries that you're working with, to the extent that they are water soluble, that's the key thing to do. So that's why you would take seaweed, for example, maybe grind it into a powder, put it into water, which is a water hydrolysis. That's the chemical term. And you're going to, through, by letting it set overnight for like 24 hours, you then absorb whatever is water soluble in that seaweed extract or seaweed powder. And then you spray the water that is rich with the water soluble components from the seaweed.
Or do you need?
So, sorry, one second. So it's not only through the stoma. Is that correct?
Yeah, there are much of the leaf surface will become porous, but the stomata are the specialized cells that are the greater cells that are open up, and they open up for two reasons. We're discussing the movement of water soluble, a water solution through the stomata, but one of the primary reasons the stomata open up is to exchange air with the atmosphere.
So is it when this, I just want to hammer it home, sorry.
Yeah.
So when the stomata relax and they open up, does that influence the porosity of the rest of the leaf? Or is it just that the rest of the leaf is equally porous at any point?
I would not say equally porous because the stomata are highly specialized cells, and they're going to open up to a much larger degree. And again, that's so that the oxygen and other gases will escape from the plant's respiratory system.
Yeah.
Okay. So the plant has been biostimulated by sunlight during the day. Photosynthetic activity has been aggressive. The metabolic system is fueled with ATP energy molecules, energy carrying molecules, and some of the byproducts of that metabolic system are gases like oxygen, which are released by the plant through the stomata of the leaf. But the leaf itself, the turgidity of all of the cells will be relaxed, especially in the evening. That's why, Chris, you hear people saying you should spray the plant when you're foliar feeding. You should only spray early in the morning before the sun really gets high in the sky, right at the break of dawn, basically. Or you should spray at night, right when the sun is going down.
Gotcha. Okay. Another question.
So
Yeah.
through the method of diffusion, you get the nutrients or the micronutrients out of the seaweed. Is there any ideal temperature of the water that you use that will do it easily? Or what's
Sure.
He's gasping the whole time.
If you're trying to pull the nutrients from, say, the seaweed, you're doing that 24-hour soak, the hydrolysis. What is there an ideal temperature, ideal condition, anything to pay attention to when you're trying to make that kind of extract?
Sure. You can if it's just a water hydrolysis, you can consider the temperature of the water, because the process of hydrolysis is breaking the bonds of the molecules that are holding the water-soluble elements in the seaweed tissue. I'll repeat that. The water hydrolysis is basically a process of breaking bonds, chemical bonds, that are holding the molecules in place that are within the tissue of the seaweed. So you're trying to liberate water-soluble components that are in the seaweed. You're using water to do that. You should grind the seaweed. You should dry it, like sun dry it, and once it is dry and crispy, that's when you grind it into a powder. then you allow the powder to be exposed to water under maybe 1 kilo of water with 20 liters, 1 kilo of seaweed powder with with 40 or 50 liters of water, like a barrel, you fill it up halfway with water, you put 1 kilo of seaweed in there, and then you create an extraction. That 50 liters of water then becomes a concentrate that you can further dilute and spray through your spray equipment. But the extraction that you're doing with water can be enhanced by starting with boiling water, because then you're going to employ heat as a component in the chemical reaction of breaking the bonds to liberate the water-soluble components from the tissue of the seaweed. So that's only talking about water as a way of breaking the bonds and liberating the water-soluble components. There are other things that you can do as well, but the most simple thing you can do is just use water. You can use solvents that are blended in there. There are various ways to process this that would be even more successful than just water. And there are certain types of solvents that can be used which increase the success of the extraction process.
So this is something that likely, if you start searching these terms online or looking into it, there will be a million different recipes and a million different ways to do this. So
yes,
this is the tip of the iceberg when you start talking about this kind of thing. And there are whole branches of agriculture that are devoted to making extracts from plant materials and then applying them to plants themselves. So.
Yes, I'm just trying to give you the science behind it so that you have a elementary understanding of that science, and then you can go from there.
Yeah, that's great, Jim. Thank you. Any other questions on this idea? No, I think, why don't we take a coffee break?
Yes.
And we'll be right back. Sound good, guys? All right. Okay, we're recording. We're good to go, Jim.
Okay. So the next section is soil physical properties. It'll be a relatively short session. We're going to cover the main components of a soil composition and give you a feel for what it means to manage soil physical properties on your farm. You'll see the graphic that I have there. Soil composition. Soils are made up of about 20 to 30% air, 20 to 30% water, 5% organic material, and minerals around 45%. The mineral fraction is basically sand, silt, and clay. Soils, as you can see here, are about half pore space and half solids. So let's make that clear. When you're dealing with a soil, it should be about half open pore space and half solid material. So we tend to think of our soils as being something solid, but really what you're looking at is an environment which is only half solid. The other half is completely open porosity. The porosity is either filled with air or it's filled with water. Soil texture refers to the composition of the soil in
Got
terms
a
of the,
Jim?
yeah,
So will the water content also will be like 20 to 30?
Yeah, I mean, this is in Curacao. Would you have the same percentages of pore space and mineral content? Water.
this analysis is a description of an ideal soil. And it doesn't matter if you're talking about your island or any other part of the globe. You're going to have soils that vary a lot. So the soils may have a larger percentage of solids, or soils that might have a larger percentage of pore space. From an agronomic point of view, either having too much of either one would represent an imbalance. In the eyes of the world of agronomy, this description that you see here is by definition what is considered ideal from the point of view of supporting plant production. But in reality, these proportions, these statistics vary quite a lot from soil type to soil type, from farming system to farming system. But ideally, any farming system should pursue a soil profile that looks similar to this. Let's just take one component, organic matter. 5% organic matter for most mineral soils in today's world would be considered fairly high organic matter. And in the case of the soils there on your island, I'm sure the organic matter content is mostly going to be less than 1%. Is that your estimate, Chris?
In some soils, other soils actually appear much darker, but
Okay.
yeah, around 1% or less.
And then if your farm management system is making an investment in increasing organic matter, this is something that you control, and you can decide how much organic matter you want in your soil to a large degree. There are soils on the planet that are considered organic soils. Most soils are considered mineral soils. But there are other soils where the organic matter might be 70 or 80%. These are called muck soils.
No.
And you usually find them where a swamp has been drained.
Is that good? I mean, question. Sorry, does that answer general questions? Okay, yeah, we're good.
Okay. So this illustration that we're looking at now is a classic part of a graphic presentation of soil composition from a texture point of view. This chart is 100% about the texture of the soil. The texture of your soil being dictated by the percentage of clay, silt, and sand in your soil. and you can determine what type of soil that you have by analyzing the textural distribution and then finding where your soil is on this graph. So if in your analysis the clay fraction of your soil is 50% and the the sand fraction of your soil is 60% and the silt fraction is 30%, you'll end up with a clay soil. You can see here that almost any soil that has 50% or more clay in it will fall into a clay category, which is the largest category here. And then the sandy soils on this end will be soils that largely have 50% or more sand. And then the silt soils will have 50% or more silt in them, and they fall in this corner of this triangle. In the middle, you have soils that are roughly evenly divided between sands, silt, and clay. So just guessing, what kind of soils do you think you have on your farm? Let's have at least a couple people make a guess as to what they have on their farm.
Marco?
Would you feel you have more clay, more sand, or more silt?
What kind of soil do you have here if you're working?
Well, LVV, gosh, I mean, it's like a clay with some sand. It's limestone that's been broken down into pieces, and then there's some sand and rock. Very little silt or loam, or silt in it, I would assume.
No clay.
No, I'd say mostly clay
Mostly clay.
with like sand and clay.
Clay.
Rock. Could you talk about where like sand and clay come from? I mean, with their whole island's made of like limestone. So like I saw some really good examples of this on Christophel of like the pieces of rock breaking down into smaller and smaller and smaller pieces until they are these mineral components. So Jim, can you maybe talk about that?
Yes.
The sources
The
of
mineral, sand, silt, and clay are the mineral proportions of your field. And sand, silt, and clay originate from what's called the parent material. And there are many types of parent material. But as parent material weathers, it breaks down into different component parts. And sand is a silica parent material. So silica is a form of naturally occurring rock that you find all over the planet. And whenever it breaks down, it will tend to become what you recognize as sand. And it can be broken down through water mostly. Water would break down the apparent material. There are other forces that can produce weathering, but water is probably the most prevalent one. And when a particulate material has broken down to a really, really small component part, it becomes a particulate of clay. And clay is all of these elements are basically the parent material breaking down to a particular size. Once you reach a range of where the particulate falls into a certain range of dimension, then that is sand. And when it gets a little bit smaller, it becomes silt. Gets a little bit smaller, quite a lot smaller, it becomes a particulate of clay. So it's a weathering process or a degrading of some of the original parent material, which are basically rocks that have weathered to produce what we observe today as sand, silt, and clay. Is that enough of an explanation?
Yeah, generally. I mean, you're gonna talk about the jar test in a second, and that'll probably make it more clear, I think.
Yes. Okay, so we're going to try to play this jar test here. Let me see here about sharing that. F, C, K. See it here. Okay, here we go.
We're not getting any volume out of it, Jim.
You're not getting any volume?
No, and I'm afraid that second email you sent me is still lacking the extra content. How about this? I'll search this on YouTube and I can try to play it from my computer.
Yes, can you copy the, on your computer, can you copy the URL?
No, that second email you sent to me still wasn't the correct one. I don't have anything after page 18 still.
Okay.
But I think I found the same video.
Today, I show you.
Yeah, found the same video. I'll just pop it up on the second.
Okay.
Oops. Let's see. Could you go back to your other view? I can't override your screen sharing for a second here.
You want me to turn off screen sharing?
Yeah, why don't you try? Actually, I think I can. Here, you don't have to do that. I can just, I got it here. Hold on.
Okay.
All right. All right, here we go.
A very simple way to figure out how much sand, silt, and clay you have in your garden.
You're good.
I'll then show you how to use the soil texture triangle to figure out the type of soil you have. This information can be very useful when you're trying to select plants for your garden, or if you're trying to figure out why certain plants aren't growing well. It also helps you figure out the right amount of fertilizer and water you need to add to your garden. For this test, you will need to get some soil from your garden. It is best to collect a shovelful of soil from several different spots and then mix it. This will give you an average soil sample for the whole garden. You will also need a clear container. and an old jar works well. Try to get one with vertical sides and a flat bottom. I'm going to use an old peanut butter jar. You'll also need some tap water. Let's get started. Check the soil and remove any stones, plant roots, and earthworm. They can be returned back to the garden. If you have hard lumps of soil, it is a good idea to break them up. It will make mixing much easier. Take the soil and add it to the jar so that it is about 3/4 full. Now add water to almost fill the jar. You want to leave some air space at the top of the jar for mixing. Place the lid on the jar and then shake. You want to mix it well so that all of the soil is broken up into individual particles. Turn the jar over and make sure all of the soil is freed from the bottom. You can also use a stir stick or spoon and really give it a good mix. Let the jar sit for 1 minute. Since sand is heavier than silt and clay, it settles in less than a minute. The sand has now settled to the bottom of the jar. Take a marker and draw a line at the top of the sand layer. Wait 1 hour. Silt is heavier than clay and will settle next. Draw a line at the top of the silt layer. Wait 24 hours for the clay to settle. Since clay is made up of very fine particles, it takes a long time to settle. Now draw a line at the top of the clay layer. Ignore any floating organic matter, like bits of leaves or stems. I've emptied the jar and can now see the marks very clearly. Take a ruler and measure the distance between the marks. Working in millimeters will make the math easier than using inches. Measure the distance from the bottom of the jar to the first line. The sand layer is 30 millimeters. Next, measure the distance between the first and the second mark. The silt layer is 22. Last, measure the distance between the second and third marks. The clay layer is 25. The soil texture, by definition, consists of sand, silt, and clay. And those 3 parts added together make up 100%. In our experiment, we measured the amounts using millimeters, but the units don't really matter since we will be converting them to a percent. Sand had a value of 30, silt was 22, and clay was 25, with a total of 77. To convert these numbers to percent, we do the following calculation. Percent sand is equal to 30 divided by 77 times 100, or 39%. Percent silt is equal to 22 divided by 77 times 100, which is 29%. I'm rounding to whole numbers, which is accurate enough for gardening. Percent clay is 25 divided by 77, or 32%. You can see that the sum of the 3 values equals 100%. These numbers tell you how much sand, silt, and clay you have, but we can take this one step further and figure out the type of soil you have. To do that, we need to have a look at the soil texture triangle as pictured here. This might look complicated, but it is actually easy to use. Since the total of sand, silt, and clay equals 100%, we only need to use 2 of these values, and I'll use silt and clay for my demonstration. On the left side of the triangle, you can see the percent clay value, going from 0% at the bottom to 100% at the top. Our soil sample had 32% clay, and I've indicated that with the blue arrow. We then need to draw a line from that point over to the silt side of the triangle, the right-hand side, following the horizontal line in the triangle. Next, we find our silt value, 29% on the right side of the triangle, as indicated with the red arrow. We then draw a line from this point to the sand side of the triangle, the bottom of the triangle. Again, following the lines of the triangle. The point at which the red and blue lines cross is our soil type. I've added a black arrow to show that point. To simplify the display, I will now remove the blue and red marks. You can see that the soil we have is called clay loam, which is a very good soil. Anything in the center of the triangle is good gardening soil. If your soil is near one of the corners or along the side of the triangle, it means your soil does not have enough sand or silt or clay. You'll have to work a bit harder to grow things. I'll discuss ways to improve your soil in a future video, but any type of soil will benefit from the addition of moderate amounts of organic material, like compost or manure. Organic matter will loosen up clay soil and add more oxygen. In sandy soil, it adds more nutrients and helps to hold water in the soil. Thank you for watching. If you want to watch more great videos about gardening,
All right. That was pretty clear though?
Yeah.
Okay. So this is a super, super simple test you can do for yourself. I mean, take this home, find the jar, do it. I mean, we teach this to our students back home. This is the beginnings of understanding your soil. So
It's the triangle.
well, it's in this presentation, so you can find it, and this will be in the notes after class, I guess.
Sometimes
Because I'm busy.
that's why
But if you are impatient with me, for example, you can find this
I'm not
online.
impatient with you, I'm just asking them.
Sure. If you want to find this, this is all over the internet. Sand, silt, clay triangle. Is there a technical term for this, Jim?
That's a pretty good term.
There we go. Sand, silt, clay triangle. Use it with the jar test. You can tell me how slow I am after you're done. Cool. All right. Other questions on that? Was that good? Okay. All right. Moving on.
Okay. You're seeing my page now?
Yes.
All right. Soil structure refers to the arrangement of soil separates into units called soil aggregates. An aggregate possesses solids and pore space. Aggregates are separated by planes of weakness and are dominated by clay particles. Silt and fine sand particles may also be part of an aggregate. There are 5 major classes of structure in soils: platy, prismatic, columnar, granular, and blocky. Here is an illustration of each one of those categories. This crumb structure here is the view. Your crops root systems will penetrate this aggregate. Water will be held in this aggregate like a sponge. This sponge will hold airspace in the soil profile, whereas these other aggregates tend to be very poor with respect to their capacity to support crop production. Okay. There's another video clip for you. There's two of them in a row. The
Yeah.
first one is observing soil structure. The second one is water movement in soils. We just play them back to back, Chris.
Okay. Yeah, and I just got the correct presentation, so I can pull them up now.
All right. Okay.
Second. Bam.
When it comes to plants, only half the growing process takes place above the ground. Here's Sunup's Austin Moore with a way to make sure your plants have plenty of room to grow below the ground as well.
Soil matters. This is where plants get nutrients and water, but the availability of those key elements depends largely on soil structure.
Usually we have about 40 or 50% of the soil volume, which is just air, and is where actually most of the processes, the physical-chemical process take part in this, actually the airspace. It's like a house where most of the action happens in the rooms rather than in the walls.
Andres Patrignani is a graduate student at Oklahoma State University from Argentina. He offered to show us how a producer might go into the field and examine soil structure using a worksheet available on our website. It all starts by digging up a block of soil with a simple garden spade.
And actually I had to measure the length. So I have a ruler here, and this is in the protocol. This is about 20 centimeters, which is a little bit less than 10 inches. And then what we had to do is to try to detect several layers. In this case, I'm gonna try to break it a little bit to see if I can find two different layers or just one. So it seems that there is a kind of a loose layer in the top due to tillage.
Patrignani will then examine each layer individually.
Now we start looking for some of the characteristics of the protocol, such as porosity, roots through the aggregates, or if the roots are clustered around the aggregates, that means that the roots cannot pass through the aggregates because maybe it's too hard, or maybe because there are not enough pores for the roots to pass through the aggregate. So that is actually something we don't want. We want the root system to explore as much as it can.
Once aggregates, or clumps, are broken down into roughly 1 centimeter pieces, you can follow the chart on the protocol and begin to classify that layer of soil.
There are some roots here, but just not too many since this is fallow now. So there are some here very small. So I'm gonna call it a 3, which is actually what usually happens in agricultural land. Most of our agricultural land is about 3 or 4, and we rarely see a class 2 unless maybe it has been in no-till for maybe 20 or 30 years.
Then Patrignani moves on to the second layer.
And I can see it's very, very hard. This is probably a hard pan due to tillage. It's about 5 to 6 inches from the top, which is usually when we pass the disc.
15 centimeters.
And so this is hard. I see no pores. This is firm. It doesn't crumble in my hand. I had to actually put some strength and some force and break it. So here we are about probably a compact soil with few macropores. And actually, if I look my picture in the protocol, it's helping me to detect that this is a similar soil than classification 4, that's core number 4. Also, the blocks are kind of angular. See, those are very angular shapes. And every time I try to break, they don't crumble. They just have sharp edges. no macropores at all in the entire block. So this is something very, very typical of a conventional till field where we don't have very much porosity compared to a no-till where we will likely find a lot of pore space, at least in the very thin layer, which we didn't find here. The soil looks much looser maybe than a no-till soil at the very top, but after 1 or 2 rains, then we have a very thick crust on top of the field, something that we don't have, for example, in a no-till field.
Once you have classified each layer of soil, a formula on the worksheet will combine these for an overall soil structure grade between 1, which is ideal, and 5, which is not. This field scored a 3.8, the average for conventional soil in Patrick Nani's research.
The question is, what do we do now? And with this information, we had to start taking some new management decisions to try to increase the soil structure because it might be limiting our crop production. So the point is that it takes time and it takes decision to do that, but certainly improving the soil structure of the soil will help us to improve and to rise our wheat yields mainly.
If you would like to take a look at the protocol Patrick Nani is using and to print your own copy, visit our website, sunup.okstate.edu, and click on Show Links.
All right, so got that one.
Let me just say one thing
Yep.
here. So texture and structure in soil physical properties. It's not possible to change your soil texture. You're pretty much stuck with what you have with regard to the fraction of sand, silt, and clay. On the other hand, you can manage your soil structure. And you do that largely by managing the organic fraction of your soil. So the biology of your soil, the organic fraction of your soil, ultimately it's the organic chemistries of your soil that will dictate the quality of the structure of your soil. And ideally, we would like for the proportion of aggregates in your soil to be dominated by crumb structures. Okay, go ahead, Chris. Let's talk about the movement of water in soil.
You got it.
When rainfall hits the Earth's surface, one of 2 things can happen. Water can run off the land, or often, with the help of sound land management practices, water can move into the soil to be an environmental positive rather than a negative. The soil itself has an influence on whether water runs off or moves into the soil. Here's a brief explanation of how and why soils transmit water at different rates, and why you should check a soil survey when you're concerned about runoff, flooding, leaching, or other environmental hazards. Water movement in the soil is strongly influenced by soil particle size, or texture, as well as structure and pore size. Soil texture is the relative amount of sand, silt, and clay-sized soil particles. Sand particles are the largest, silt is intermediate, and clay is the smallest. Water moves more quickly through the large open macropores found in sandy soils than the smaller pores of silt, or the much smaller flat-shaped micropores in dense clay soils. Soil structure also impacts water movement. Water moves more quickly downward in soils with granular structure than a soil with platy structure, which forces a longer indirect path downward. Other structures include prismatic and subangular blocking. Water is nearly always moving in the soil, and it can be in any direction simultaneously. Gravity is the dominant force that moves water downward. Restricted soil layers of compacted soil or bedrock are among the reasons water moves laterally. Capillary action, the traction of water into soil pores can move water in any direction. Gravity is the primary water-moving force in saturated soils, while capillary actions are the primary forces in unsaturated soils. Capillary force is greatest in soils with small pores. Water moves more slowly through these soils. Well, that's a brief explanation of what a soil scientist calls saturated hydraulic conductivity. In simpler terms, the capacity of a soil to transmit water. Since downward moving water carries nutrients and can carry contaminants into underlying groundwater, soil percolation rates are important, choosing sites for septic fields, landfills, and other waste burials, as well as underground storage tanks and other uses. The information is critical for planning soil drainage, irrigation, and tillage systems, as well as other crop management practices. Get the information you need on water movement rates and other soil properties from a soil survey of your area on the web at www.soils.usda.gov.
All right.
Okay, so that's this topic of water moving in your soils. And you know, it's one thing to irrigate a field, but it's really something totally different to manage water after it enters your field. How you handle your soils, especially your soil structures, will have a critical impact on the volume of water that you need to support crop production. If you invest the time, energy, and money to improve the soil structure of your soil profile, you will tend to save money with respect to nutrient that you are needed in the field, as well as irrigation water that you add to the field.
We have a question, Jim.
Yeah.
Yeah, so when you're planting, you want the water that comes to your soil, that it stays also a bit longer into your soil.
Oh.
Clay texture will hold the water longer.
Yep.
However, you don't have enough space and enough space for the roots to grow.
Yeah.
So it's kind of contradicting the thoughts that I would rather have a clay form of soil to hold the water, but my plants cannot really grow the roots.
Clay can be, well, I'll let Jim handle that one. So it's a contradicting thought to think that clay does the best job at holding water in the soil. However, plant roots have difficulty penetrating overly clay soils, right? So, because it's too tight. So, would you like to comment further on that idea?
Yes. It's not really the clay that's the problem. It's a lack of structure in the soil that's the problem. If you have a tight soil, a clay soil, just like the video clip in the earlier video clip stated, if your soils tend to fall to one end or another of the triangle, into any of the corners, let's say your soil falls into the corner of the triangle, that indicates that you have a clay soil. Or it could be a sand soil, or it could be a silty soil. Soils that tend to be on the extreme areas of the triangle are more difficult to manage, and they will have their own specific issues. So in the case of a clay soil, what do? Your soil is too tight. you have to add organic matter. What's the value of that organic matter? There are chemistries in the organic matter. There are chemistries that might be produced by biological life in your soil. These chemistries, especially polysaccharide type chemistries, are valuable in that they're highly interactive with clay particulates, and the technical word is flocculate. They will flocculate clay, which means that they restructure the clays progressively such that a greater and greater proportion of the aggregate formations in your clay fraction of your soil will be in the form of crumb structures. And as you increase the fraction of your soil aggregate distribution in favor of crumb structures, then those crumb structures alleviate and minimize the problem with the clay soil. So you're not really dealing with the clay, you're dealing with the structural integrity of your clay. And increasing the crumb structures in your clay is the solution to solving a problematic clay soil. Does that make sense?
Where can I find the polysaccharides?
Yeah. Yes, it does. And the immediate follow-up question, where can you find polysaccharides?
Polysaccharides are a chemistry that you find in humus. You've all heard of humus?
Yeah.
Is there anyone who has not heard of humus?
You want to just elaborate on that for a second?
Yes. So humus is organic material where the organic material that you've added to your soil has broken down to the point where it is no longer distinguishable. And once organic material is broken down to a stage where the rate of decomposition has slowed way down. So raw organic matter may decompose at a rate of decomposition that's fairly high. Your microbiology, the biology of your soil in general, break down organic matter. So the rate that takes place is very critical in measuring and defining the stages of organic matter in your soil. When the rate of decomposition has come to the point where it is relatively slow and the organic matter is no longer changing, and you can no longer distinguish the original source of the organic matter, you begin to describe that quality of organic matter in that stage of evolution as humus. Humus is that organic matter which contains chemistries that are capable of interacting successfully with clay to form crumb structures. The chemistry in humus that's largely responsible for those chemical reactions with clay to bind them together to form crumb structures. That chemistry is called polysaccharide. That polysaccharide is often described in soil science as nature's glue. It glues particulates of clay together to construct aggregate formations. These aggregate formations are called crumb structures. They're porous, they hold air, they hold water, roots can grow through them, and this construction of crumb structures is something that a farm manager needs to do He needs to be responsible for that. You need to invest in that. You need to understand how to do that, because those crumb structures are important to all of the soil types, regardless of where you fall on the triangle. All of the soil types that are on that triangle need to be managed in such a way that you are always increasing the fraction of your soil that falls in the category of crumb structures.
Would it be fair to say that soil biology also contributes to the polysaccharides?
Yes, yes, I mentioned that also in my list. It's the organic matter, but it is the biology is responsible for breaking down the organic matter. And the biology may break down the organic matter directly to a point where it becomes polysaccharides, or the biology may consume elements of the organic matter and exude, which means they excrete chemistries in the form of polysaccharide.
They poop it out, basically. One way to think about it. Does that make sense?
So it's good to have like a subsoil which is made of clay if you're in a dry climate to hold the water, and on top of that you have a layer of soil in which to cultivate.
Yes and no, because if the water goes through that well flocculated soil, the crumb structure, if it gets down to that clay layer and then can't move any further, it'll stay there and create an anaerobic environment. So it will kill soil biology, it will change the structure of the soil, it will destroy nutrients in that layer. So if you have a compacted layer below good soil, it can still be detrimental to any roots or plants or biology that come in contact with that area.
And does it matter how deep that is? So
Yeah.
if it's like if the clay is much deeper, then would it still affect the topsoil?
Is there a depth at which a hard pan, be it rock or clay or whatever, becomes less important in crop management?
Well, it depends on the crops you're growing and how deep the roots tend to go. Legumes will tend to produce a root system that goes much deeper in the soil compared to grass crops. And there are two types of crops. In agronomy, we would define crops in two categories: grass crops and legumes. Grass crops will have more shallow root systems. Legumes have a taproot. The taproot will go much deeper than the taproot of a legume will go much deeper than the root system of a grass crop. And so to answer your question, it depends on what type of plant that you're growing there, whether it's a grass or a legume. And in the case of grasses, hard pans are less problematic. But in the case of a taproot, one of the values of taproots with regard to hard pans in your soil profile is taproots tend to break the hard pan.
Does that make sense? So like trees would be another example of a crop that might be impacted by a hard pan. But depending on the kind of tree, if it has a taproot, it could punch through. Any other?
Or die hard plants.
Or a die hard plant. But there are ways to relieve compaction layers using a broad tool. Joshua has one. We're going to demonstrate it at some point here. But it's a it disturbs the soil very little, so that you can punch down deeper than normal tillage might normally get into the soil and break a hard pan open, allowing water, air, biology, humus, whatever, to get down lower and start acting on that clay or on that compacted area. In larger scale agriculture, there are other tools that are similar. They have a less of an impact from a tillage perspective, but reach much deeper into the soil. So there's mechanical ways to deal with compaction. There are chemical ways to deal with compaction. There are biological ways to deal with compaction. Some combination of the three, choosing an effective way to use those together is, as Jim keeps relating, it's a management decision. Something you have to decide.
What about the organic way is using humus, right?
What?
Humus is
Yes.
the organic way, or
yeah, you can think humus and organic matter, though not exactly the same, are often interchangeable when we're talking about soil.
I had another question. It was about the
Another question.
The flow of water.
Yeah.
The gravity has its the most force on it, but
Yeah.
through capillary circulation, water can go up again.
Yeah.
So that means that if on top of the soil you have moisture or something that attracts the moisture, the water that is in the soil can circulate and come up again.
So he's asking about capillary action and how it draws water up again. What are the conditions that would cause capillary action to draw water in a particular direction?
Evaporation.
yeah.
This is called in soil science. This was called negative bars of atmospheric pressure, and there is a gradient between the air above the soil and the air in the soil. And if the air above the soil is dry, it will tend to create a force, an evaporative force that's like a sucking action that will pull water and water vapor up through the capillaries of the soil profile to the point where the negative bars of pressure are trying to create an equilibrium. So it's just the force of nature really to pull the water back up through there in order to make the air above the soil have the same humidity as the air in the soil. So it's evaporative pressure.
So if we cover our soil and prevent evaporation, then we preserve water. So
Right.
we encourage water to come up through the soil by uncovering our soil and allowing it to dry, which pulls soil from below ground up because it's trying to create a equilibrium, a balance.
And the water that's beneath, when it comes up, does it draw minerals up also with it?
I think it would. Yeah, does the capillary action draw minerals up with it, nutrients?
Nitrogen, yes. You can lose nitrogen through that process. The other minerals, no.
Yeah, but this isn't necessarily a way you'd want to try to get nitrogen to your crops, would it?
Make you think, Professor.
I don't know if you heard me. Did you hear that last one, Jim?
What was it?
You didn't stump him yet, so sorry, guys. So if capillary action, carries nitrogen upwards through your soil, would this be a way to get nitrogen to your plants?
No.
Because the total quantity would be probably not that much compared to how much water you were losing.
Yes.
Yeah.
That's correct.
It'd be a waste. you keep your water.
Keep your water is more important.
You're going to get a lot more nitrogen from the organic matter in the soil and from the organic matter on top of your soil, holding that moisture in and slowly breaking it down, because then the life in the soil, the natural processes creating humus in the soil can act on organic matter higher up in your soil, because there's more moisture, which is necessary for a lot of this chemistry to happen.
Okay,
Yeah, we're good.
let's go on to air movement. A few comments. The movement of air is very important, and we've been discussing it here already. Let's make a couple of points about air movement. You can see on the left-hand side is a graphic here that shows a aggregate, and inside that aggregate you have organic material. You have various pieces of clay and quartz material, which could be considered silt. You have microorganisms that are growing inside and around the aggregate itself. You have water that will store inside the aggregate, and you have air that's stored inside the aggregate. This is an illustration of how important an aggregate is to a soil profile. The water that is retained inside the capillary action within the aggregate is very important water, especially when water becomes scarce and your soil gets really dry, and the dry condition threatens your plants. If you have invested the effort to create a large fraction of crumb structures like this in your soil, they hold water. These are small capillaries, they hold water, whereas the capillaries on the outside of the aggregate will tend to lose water to gravity. Air is very important for the biological life in the soil. Factors affecting soil aeration include the texture of the soil, whether it's sand, silt, or clay, the organic matter content of the soil, and its interaction with clay in order to form aggregates, and the bulk density of your soil, which is basically a measurement of porosity. Soil aeration is what we're talking about. Oxygen goes into the soil, CO2 goes out. Plants release CO2 through the root system from the respiratory process. In the root system, plants release oxygen from their leaves, but they release CO2 from their root system. Air is an important part of any soil. Without enough oxygen, plant roots do not grow well, and this affects the health of the whole plant. Good soils may have up to 25% air. Soil air is held between the spaces between the soil particles. So this is our conclusion on soil physical properties. It's a brief introduction to some of the principles that are important to you as farm managers, having to do with soil texture, and more importantly, having to do with soil structure.
We got a question here.
Okay.
Is it good that I can that you can through the dirt you can pass like what is it? Like sticks, iron sticks, just to open up the dirt. Like,
Is it good to like push things into the soil to create aeration?
Yeah, just to put air. Let's say that soil there, I have like an iron stick.
Yeah.
And I will like loose up the soil a little bit.
Yes. Yeah, that's good practice. If you find that there is a compaction layer in your soil, using things like an iron rod shoving it into your ground could help create aeration. So like I was commenting a little earlier, there are like tools designed for this. You don't need to just be hammering rods into your ground. So that's something we can talk about a little bit more in our workshops.
Can you use like wooden sticks, like branches, break them off, like stick them in the ground, break them off? But that's what I do sometimes to like open the soil.
Yeah, I mean, if you're shoving branches in the ground and breaking them off, it's gonna.
Branches, but little twigs, like.
If you're shoving little twigs into the ground, they're probably not breaking much compaction. If you're capable of doing that, then your soil's probably okay. When you start encountering the kind of force where the stick starts breaking off, that's a change in the bulk density, I suppose you could say, how compacted that soil is. So that would be a way to measure where your soil changes. And then depending on how deep that is or how thick your stick is, that could be something to make a decision on. You're probably going to have a better time of making those decisions by using shovel and digging straight down, so you can analyze it better than just putting a stick in the ground. Other questions? Marco, did you have one? No, you're good? Yeah, go. All right. I think that's it on questions, but we are out of time.
Okay. All right. At some stage, Chris, if you want to hear the stories on plant protection technologies, that's a presentation that we can make at some point. But I'll leave it to you guys to decide.
That'd be great. Yeah, I think the next section coming up is all about that. Well, it's about pests and organic protection, so it'd be great if we could slip you in somewhere in there. So.
All right. So just chase me down wherever I'm at. I'm in India today. Wednesday, I'm flying to Egypt.
Wow.
They're impressed.
Enjoy for us.
Okay.
Lots of pictures.
Well, have fun. Travel safe. Sleep a lot. Appreciate it, Jim.
All right. Thank you.
All right.
Bye.